Okay, so we're going to work a couple of examples here, probably in a couple of videos, at least two if I had to guess. But we'll get started here. Got my timer going. I'm going to stop share. I don't think we need it right now because we're just going to work this out on paper just like I would on a dry erase board if I were in the classroom. So here we go. Example. Example. I'm going to go ahead and write out the problem statement like you might see it in a textbook. You don't have to. We'll talk about what you would really need to do for my class. I don't know, what if you're taking somebody else's thermodynamics class, maybe they want you to write out the entire problem statement, and that's up to them, I guess. We have a 400 cubic meter per second of water. So it's not, I guess there's not an A there. 400 cubic meters per second of water flows over a falls, over waterfalls. It's probably not the right way to say that, but that's what I've got written down. The average speed of the water is 2 meters per second. The waterfall is 30 meters tall. What is the total macroscopic energy flowing through the falls? Sometimes it's probably this simple thing we could, this kind of thing we could draw a very simple diagram of. Right? Channel your inner Bob Ross here if you know who that is. If you don't know who Bob Ross is, well, I don't know what you're doing with your life. No, I'm kidding. But if you want nice, relaxing, Bob Ross is the guy with the afro that paints the cool mountain scenes. So just channel your inner Bob Ross. And if you don't know what I'm talking about, just go look up Bob Ross videos. Um, yeah. So we're just going to draw a little mountain stream here and a little waterfall, and it maybe collects in a little pond here. And I'm very much channeling my inner Bob Ross. If you don't know what I'm doing, I'm trying to talk in a very calm, soothing voice. Maybe there's a little woodland creature over here on the bank, and um, yeah. Anyway, we have a waterfall, right? Some kind of waterfall, making some mist as it plunges into this lake here. Yeah, and it's 30 meters tall, and it's coming out of here at 2 meters per second. And so we're given some information here. What do we know? We know we've got the speed. Again, that's v without a cross. Speed is 2 meters per second. You're given a change in elevation. Z2 minus Z1 is 30 meters. They've given you this other quantity up here, right up front, 400 cubic meters per second. Look at the units on that. Look at the units on that. What is that telling me? That's volume. That's a volume divided by a time. Guys, I'm not kidding when I tell you, I see people on the final calling this m dot. That is not m dot. That is volume per time. That is v dot. Right, so that is V dot. And a problem statement a lot of times won't tell you the volumetric flow rate is 400 cubic meters per second. They're going to expect that you can look at that and say, oh, that's volume per time. That means that's a V dot. That's a skill that you will pick up. And if you don't pick it up here, you'll have to pick it up before you get to the workplace because not everybody's going to speak the same language, literally and figuratively, when you're working with clients and other engineers sometimes. So You're gonna have to figure out what they're telling you and not telling you, right? And that's why I always say, look, you don't have to write the whole paragraph for my purposes. Write what you're looking for. Find the macroscopic energy. That's it. That's all I would really need you to write here for my purposes. And so that's going to come down to, okay, well, what are we looking for? We're looking for the rate of microscopic energy flowing through the falls, basically, right? So how would we do that? Well, what we can do is we could try to figure out, um, I can maybe figure out the macro. I mean, first I need to know what the heck is macroscopic energy. What is that? Well, we talked about that. That is your kinetic energy plus your potential energy, right? That is your energy macroscopic. That's a definition we talked about briefly. We didn't dwell on it too long, but we did mention that a few videos back. That's the macroscopic energy. It's kinetic energy plus potential energy. Now, I don't have a mass here. I don't know the mass of flow here. I don't have a total amount. So what I'm going to do is I'm going to look at this per unit mass. So little e is going to be little ke plus little pe. So I'm going to find that first. And what I can do then is say, well, again, the kinetic energy is just like it was in physics. That's mv squared over 2 plus, and then the potential energy is going to be mgz. And then, so with the potential energy, then it's just going to be those divided by mass. That's v squared over 2 plus gz. Well, we know these things, right? And basically, we're looking at, okay, how far will it fall? That's my z. How fast is it going when it comes off? That's the 2 meters per second. So these are basically kind of the potential that it has right as it comes off the falls, right? So that's easy enough. I've got 2 meters per second. That's going to get squared divided by 2. So now I'm plugging in numbers because I'm down to, I know all this, right? I know G, I know V, and I know Z, right? G in metric units, we can call it 9.81 meters per second squared. 9.8 is fine. And times 30 meters. I keep a calculator app on my phone here. And it wants to know if I want to upgrade. I do not. Okay. Um, so let's see here. 2 squared divided by 2. And here's where I would say, hey, have your calculators out. Help me out as we go. And obviously I could I could say that, well, that's 2, duh. Uh, plus 9.81 times 30. Right? And so yeah, so my sum there, what I'm gonna have, E macro. So normally, again, I would have you guys calculate this out for me and sit in the classroom, and we'd agree on a number when everybody comes up with the same thing. Now, what are our units here, right? What are our units here? Well, notice this is meters per second. That's getting squared. So that's meters squared per second squared. And by the way, before you add these together, you should make sure the units are the same because that's the rookie mistake is just adding apples to oranges and they're not the same. So this is meter squared per second squared. This is meter squared per second squared. You can also say, hey, Steve, it's the metric system. The units always work out. Well, that's true until they don't. We will encounter times throughout the semester where even in the metric system, units don't work out all the time. A lot of times it's just a magnitude of 1,000 that we're off, or adding kilos to megas or something like that. But if you learn how to make sure your units work in the metric system, when you do get to the English system and the imperial system, it works out. It makes it a lot easier to work with. All right, now is this what they asked for? Well, the problem's not very clearly worded, honestly. This is probably okay. We could probably box this in and call this our final answer. But you know what? They did tell me the rate at which water flows through this. Now, they didn't tell me, they told me the volume. They told me the volumetric flow rate. Well, here's the thing. I could also tell them, well, you know what? I can tell you the rate at which the macroscopic energy flows through the falls because that's going to be the mass flow rate. And this is the energy per unit mass. So the mass flow rate times E macro. And I notice I've skipped ahead a little bit here. I should back up and notice these units. Technically correct, but not a unit of energy, by the way. So a lot of times I'm probably not going to let you keep that. Give me a unit of energy or some kind of energy, whatever's appropriate. What is little e? What units would we like here? Well, this is energy per unit mass. So I'd probably like something like joules per kilogram, or something of that nature. So what you can do is just kind of off to the side, you can do your units, right? I'm going to write in my margins my engineering paper, which is an absolute cardinal sin. You're not supposed to do that, but it's okay. This is just notes off to the side. So what I'd like is if it's energy, so maybe I'd like a joule, which remember a joule is a Newton meter. A joule is force times distance. That's a Newton meter. Um, well, okay, let's break this down. So Newton breaks down into a kilogram meter per second squared. That's mass times acceleration times a meter. So a joule is a kilogram meter squared per second squared, which means that a joule per kilogram is a meter squared per second squared. Again, you can normally assume that in the metric system that the units just work out. And a lot of times that works out okay until it doesn't. And if you're not in the habit of making sure your units work out, that's how we crash Mars rovers, or in our line of work, honestly, that's how we kill people. Unit mistakes can kill people for what we do. Scientists don't have that worry, but we do. So you can assume the units just work out magically, and I'm going to take a lot of points off when they don't. So don't. And if you get in the habit of working out in the metric system, I promise you, the English system still is not going to make a lot of sense, but it makes it easier at least. All right, let's figure out the rate at which energy is flowing through this thing, because I know now the energy per unit mass, and I can figure out the mass per unit time because I know the volumetric flow rate. We know m dot is going to be density times that volumetric flow rate, which we know, times this little E macro. So I know all these now, right? Or at least I can make an assumption about it being, right? I can assume up here. I've already made an assumption about gravity. I don't normally write that down, but you could. But I'm going to assume that the density of water in the metric system is about 1,000 kilograms per meters cubed. So the rate of macroscopic energy flowing through this waterfalls then is going to be this density, which we found to be about 1,000 kilograms per meters cubed. That's what we're going to assume. Multiplied by the volumetric flow rate, which is given up here, 400 cubic meters per second. Multiplied by this 296.3 joules per kilogram that I've calculated a second ago and made sure the units work out like a good engineer. Right, it's 296.3. All right, let's back up here so we can see what I'm doing. 296.3 times 1,000 times 400, and we get a really big number. And that's okay. Sometimes we get a big number. Okay, so let's move this up. Try to get everything on the screen. The rate at which, and by the way, 400 cubic meters per second is an enormous stream. It's a big river flowing through this thing. So it's a lot of energy. What do we got there? That's 1.18. We'll say 185. That's probably too much. We could say 1.19 just as easily, but I would not say any more than that. And we're going to say times 10 to the 368 times 10 to the 8. It's going to be the number there. And the units there, the meters cubed go away, kilograms go away. I've got joules per second, that is watts. So this is actually 0.119. I'm going to call it megawatts. 0.119 megawatts would be fine. This is correct. This is perfectly fine. Either one is okay. Yeah, hydroelectric power is a real thing, but you do have to have a really big volume of water flowing to make it work. Okay, so just I thought this is a nice flow rate problem to work through, kind of introduce concepts of energy, work our way through unit conversions, or at least making sure the units work in metric system. I've got another English unit problem with efficiency that will work in the next video then.